Hello. Hopefully your familiarity with alkyl halide substitutions is getting better and you're getting more comfortable with those types of reactions. But alkyl halides can also undergo eliminations, and Unit 8 is going to look at eliminations. And just like substitutions have SN1 and SN2 pathways, eliminations have E2 and E1, bimolecular and unimolecular. And for this video, we are only going to focus on the E2 pathway. There's a lot of terminology for the E2 pathway that will require its own video. Now, taking a look at the illustration, you want to keep in mind when you do an elimination, you're eliminating definitely the halide, but you're also eliminating a hydrogen. And a lot of people get confused about which hydrogen to remove to make the double bond. Eliminations will make double bonds, and you'll see that in just a bit. Whenever you think about this unit, elimination, please also add beta hydrogen, because all the eliminations that you'll be doing are going to be beta hydrogen eliminations. Beta hydrogen eliminations. And that's why I drew a betta fish. Okay. Let us jump right into it. This is the first video for Unit 8, looking at alkyl halide eliminations. And let us start with let's start out with this alkyl halide. Okay. Those of you who are very good at substitution, if I gave you this reagent, if your mind is on substitution, you'll visualize this OCH3 anion. Okay, that's step 1, understanding that this is an anion, or it separates into its anion and its cation, and you'll attack that carbon and take out the bromine, and you would get this product. That is definitely the substitution product, which you probably learned about in Unit 7, alkyl halide substitution. But this can also act like a base. And if you remember beta hydrogen elimination, you're not going to remove the hydrogen off of this dot, because the carbon that's attached to the halide is called the alpha carbon. Alpha carbon. It's the carbon next to the alpha carbon that's the beta. And in this case, we only have one beta carbon. It's the one to the left. Okay. So I'm not going to draw the mechanism, but take a look at my product and you figure out, did I remove a beta hydrogen? There are 4 carbons. Okay. Take a look at this alpha carbon. Okay. It has 2 hydrogens attached to it. It still has 2 hydrogens attached. So there's your alpha. But take a look at the beta position. The beta position originally had 2 hydrogens, and now it only has 1 hydrogen. That's why I call this, or not I, but that's why this is called beta hydrogen elimination, if you want to get really specific. And we'll put it here. In this unit, we are only going to focus on eliminations, even though if I give you sodium methoxide, you actually get 2 products. Okay. Some professors will test whether you understand that you get 2 products. Okay. And some professors will test these concepts separately and just ask you either to draw the substitution product or draw the elimination product for a particular problem, but not both. Okay. But I don't want to lie. When we do these reactions, and we're only drawing the elimination product, for a lot of those reactions, the substitution product can also exist. But I am not, at least for a while, not going to say how to determine whether you have a mixture or whether you have one or the other. Now, when you have an elimination, you're almost always making an alkene. Sometimes you'll be making an alkyne, which is a triple bond, but we haven't reached that unit yet. So if you see an alkyl halide and it goes to an alkene, you did an elimination reaction, and specifically you did a beta hydrogen elimination with a base. Okay, so going to this pathway, we're using this NaOCH3. It's the same reagent, okay, as a base. Over here, for this product, it's acting as a nucleophile. Okay. All right. So let me put that disclaimer. Okay. Let's look at the bimolecular pathway. The bimolecular pathway is called E2. And do you remember what happened with SN2? With SN2, the leaving group left at the same time the nucleophile attacked. So with SN2, two molecules were involved in what's called the rate determining step, the slow step. No carbocation was formed in an SN2 process. Well, same thing with E2. SN2 and E2 are similar in terms of their kinetics. Okay, you need two molecules to get through the rate determining step. But let me show you this one. Okay, this molecule here. Alright. You notice that this molecule has two beta carbons, one on the left, one on the right. We're going to use a strong base, and another strong base could be NaOET. We're going to draw the products, and then I'll show you the mechanism. The thing is, we have two beta carbons. So we can eliminate the hydrogen on the left and make the double bond between the alpha and the beta on the left. We could call this beta 1 and call this beta 2. So when we eliminate the hydrogen off of beta 1, did you notice where the double bond occurred? It occurred between the alpha and the beta. So if we eliminate the hydrogen on beta 1, we're going to make a double bond between the alpha and the beta 1. Does that make sense? It will make more sense once we look through the mechanism, but I want us to learn how to get the product quickly. What are the tips for that? Now, there's one slight issue. I chose to draw the trans alkene. Okay, but honestly, this bond right here is twisting. It's rotating all the time. And at some point, this methyl group will be pointing up. This methyl group will be pointing up when we lock the molecule into its double bond species. So what does that look like? When it's locked up, and the methyl group is up like this, and the double bond forms while the methyl group is up, do you see we get the same alkene? We get the alkene on carbon number 2, right? Numbering it from the right. But now we have the cis version. Now there's one other product. What if we remove the beta hydrogen off of the beta 2? So I'll put beta 1 there. In that case, we have this. alpha, beta, 2. Do you notice that there's no cis and trans here? So we're not going to draw two stereoisomers, one cis and one trans, because there is no cis and trans. Okay, which is a major product? When you have a strong base, you got to remember, this is a salt. We have Na plus, O, Et minus. Et stands for ethyl. It's an abbreviation. Okay, so this is our base, and it's a strong base. And we're going to say that all oxides, right? This is ethoxide. All oxides are strong bases. And we are eliminating. That strong base is going to grab one of these protons, either off of the beta 1 and off of the beta 2. So that could be ethoxide, it could be methoxide, it could be propoxide, okay, any oxide. What about the major product? The major product is the double bond that's most stable. You know that mono-substituted is less stable than di-substituted. And this is also di-substituted. If you need to review that, I believe that's, oh boy, I think that's Unit 3, where I talk about E and Z, cis and trans, and the stability of the double bond. Okay, so di-substituted is the winner, but between these two di-substituted alkenes, trans is more stable because you don't have steric bumping between groups that are kind of close together in the cis version. This is the major product. For my class, when you do an elimination, I do want you to draw all the possible alkenes and then circle the major product. The major product actually is called the Zaitsev product. And we are using Zaitsev's rule. Okay. You have Markovnikov's rule when we did addition reactions with alkenes. Here we have Zaitsev's rule when you're trying to figure out the major product out of a mixture of alkenes. And Zaitsev's rule clearly states that the major product in an elimination is the most stable alkene. Okay. Alright. Let us. Now that might seem obvious, right? The major product is the most stable product. But chemists are always looking for other outcomes, unusual outcomes, and actually we could get the anti-Zaitsev product with a little bit of change, but I'm not going to show that just yet. Okay. Right now, let's focus on Zaitsev and be able to identify the most stable alkene, which will be the major product. So the E2 mechanism, I think I could squeeze it in here. For E2. Okay. And we'll draw it for the major product. Okay. It's one step. Just like SN2 was one step. Are you making these connections between things that you've been taught before, SN1 and SN2? This is E2. We'll look at E1 in a different video. The major product is removing the beta hydrogen off of this beta carbon on the left. You have to draw all the hydrogens on that carbon if you're going to remove one of them. Okay, you just can't draw one. You have to draw all of them. If you draw one, you draw all. Not all in the molecule, all for that carbon. That's your beta. You could label it if you want. Okay? We have a strong base. And the base, again, was ethoxide. So look at this cascade. The leaving group's going to leave in this step, but with the help of the base. And I want to really emphasize this is a strong base, because I'll give it away. The E1 mechanism is when you use a weak base. So if you can see that it's a strong base, you'll automatically know that it's an E2. Okay. And I'll write that on the next page. But here's the mechanism. Base grabs a proton. Okay. What proton? The beta proton, or the beta hydrogen. This bond collapses. So those two electrons make the pi bond to make the double bond, and that leading group leaves. Your product. And since I drew the mechanism while this methyl group was down, okay, I could have rotated this bond and had the methyl group up, but I wanted to make the more stable disubstituted alkene. I wanted to make the major product. So the major product again is that. What else do we have? We have the base. We got the hydrogen, so that's the, we call it the conjugate acid, plus the Br minus. For a mechanism, I do want people to draw out all the products at each step. But for filling the product, just give me the just give me all the alkenes possible, and then circle the major one. Now, why is this E2? Because the rate equals K, but it's dependent on these two molecules, because since we only have one step, this is the slow step. Do you remember what RDS stands for? Rate determining step. So it's dependent on two molecules to get through the RDS. So the rate constant, not the rate constant, the rate is going to be dependent on both the alkyl halide concentration. Remember the square brackets mean concentration, and the concentration of the base. Okay. Now, let me write something down so we know that when we find a strong base with an alkyl halide and we do an elimination, we have to do an E2 elimination. And I'm going to sum that up pretty easily here. All primary, secondary, and tertiary eliminate via E2. How? With strong base. And I already showed you what is a strong base, or at least gave you an example of a strong base. It's all the oxides. Okay, but you have to recognize that it's an oxide. Okay, you know, if I had HOET, that's not a base. HOET is an alcohol, right? That H doesn't just come off by itself. This one sodium will come off in solution. It will separate. It's ionic. HOET is ethanol. It's not ionic, and you won't get the anion. Okay. That should sound familiar because with substitutions we learn good nucleophiles and poor nucleophiles, anionic nucleophiles and neutral nucleophiles. Okay. So I won't belabor the point. You gotta remember this. E2 with any alkyl halide with a strong base, okay, or I should say any alkyl halide with a strong base eliminates via E2. See, that's different than substitution. Do you remember that substitution was dependent on how crowded the alkyl halide was? And if it was very crowded, like a tertiary, it's more likely to do SN1. For elimination, all we have to remember is the strong base, and we know it's E2 regardless of the type of alkyl halide. Let's give another example. And me just make sure I'm not missing anything I want to cover. Yeah. Okay, yeah. Let's do another example. Let's do chlorine here. And, how about this? Cool. And how about another strong base? Another strong base could be NaNH2. Okay, so this is not an oxide. You still have to recognize this as a strong base, because why? Because when you put this in solution, the sodium plus dissociates, and look what you're left with. You know why that's a strong base? Because the conjugate acid is so weak. Do you remember the phrase, strong acid leads to a weak conjugate base? Well, it's vice versa. Weak acid leads to a strong conjugate base. NH3 is a weak acid, so its conjugate base is going to be a very strong base. Okay. Hopefully you could follow that line of reasoning. Strong base. Look how many beta carbons we have. We have alpha, we have beta, beta 1 maybe, and beta 2. What are your possible alkenes? Your possible alkenes? Why don't you try it? And remember, you're always making a double bond between the alpha and beta, but you have to take care of all the betas, right? Either the one on the left and the one on the right. Okay. Go ahead and draw the product. Pause the video, give yourself 2 minutes, and just put a double bond, right, between the alpha and beta. Now, just be careful. That beta carbon has to have a hydrogen to eliminate. This is called beta hydrogen elimination. So if there were 2 methyl groups here, it wouldn't make any sense to make a double bond to the right, because that carbon will have way too many bonds. It would have 5 bonds. Okay. Pause the video, draw me the products, and circle the Zaitsev product, the major product. Okay. I have 2 beta carbons, and there's no cis and trans, because we're in a ring, a small ring, a 6-membered ring. So all of them are going to look cis. So we have that because we eliminated the hydrogen off of beta 1. But if we eliminate the hydrogen off of beta 2, what are we going to get? We're going to get that. Alpha, beta 2. And the major product is this one. Okay, pop quiz. Is that a mono-substituted, di-substituted, tri-substituted, or tetra-substituted alkene? If you put your dots on the carbons of the double bond, that purple dot has one group, that purple dot has a group going to the right, and the group going down. This is tri-substituted. And this is Zaitsev's product. And it's the major product. Now, for the last 7 minutes, 5 to 7 minutes, I want to talk about actually that. That's the Zaitsev product, and it's a major product with this base. Okay. Right now we have 2 examples of bases, the oxides and the N-. Both of those are strong bases. This product, the less stable, has a name. It's called the Hofmann product, or the Hofmann. I gave it away. We are going to make the Hofmann, the product, in just a bit, but this is called the Hofmann Alkene, the less substituted. And we call this the Zaitsev product, or the Zaitsev alkene. Okay. Let me show you how to make the less substituted double bond. And I'm only going to teach you one way to do this. And let's go back to our classic secondary alkyl halide. Okay. if we use a base called potassium tert-butoxide. Oh my goodness, what is that? Okay. Potassium is K+. Okay, so that's a group 1 metal, just like sodium, and so you're going to dissociate it. And then we have an oxygen. Remember T-butyl? The crow's foot. It's this. Okay. So that's a strong base. I told you that oxides are strong bases. But it's also a bulky base. Crowded. The thing about a crowded base like potassium tert-butoxide, or another way you could see this is you have a C and you have 3 methyl groups around it. Okay. Sometimes they draw it like this. It's kind of confusing. These are parentheses, actually, right? I think that's correct for that molecule. You could double check me. But when you're very bulky, it can't hit this hydrogen. Okay? When you're very bulky, it goes for the less crowded hydrogen. So the bulky base goes for, I'll put an X here, goes for this beta on the right. It's less crowded. Go for less crowded beta hydrogen. Sorry, I'm a little rushed. Beta hydrogen. You're still probably going to want, your professor will probably still want you to draw all the alkenes, because you do get a mixture. Okay. So let me draw quickly your 2 disubstituted, and here's your monosubstituted. Do you see how if you're very bulky, and the only bulky base I'm going to teach you is this potassium tert-butoxide that can be represented this way, that way, or this way, you're going to pluck off the beta hydrogen on the less substituted carbon, or the least substituted carbon. Least substituted beta carbon. Remember, it has to be beta. When you use a bulky base, like potassium tert-butoxide, you're not going to go for the most stable alkene. You're going to go for the least stable, the less substituted alkene. And now this is the major product. And it is the Hofmann product, or the Hofmann Alkene. Okay. As a reminder, when we used a non-crowded base, non-bulky base, you go for the alkene that is the most stable. That's the Zysef product right there. Out of these 3, that's the most stable. Out of these 2, this is more stable. This is tri-substituted, and that base is not bulky. It's not crowded, so we go for the Zysef product. When we use a strong base that's bulky, the only one I'm going to teach right now is potassium tert-butoxide. You got to resist the instinct to circle the most stable alkene. You go for the less stable alkene because it is the less crowded. It plucked off the less crowded beta hydrogen. Right? Remember, this is primary carbon. This is a secondary carbon. So the primary carbon is less crowded. Good. I think that's what I wanted to get through. Now, we only went through, right, the E2 pathway, the bimolecular pathway, and here's the mechanism here. What you can do is you could ask yourself, or challenge yourself, draw the mechanism for this reaction. It's the same mechanism. It's just that you're plucking off now the beta hydrogen on the right. Draw a mechanism of above reaction. Okay, that is your homework. Okay. Next video, I think we're ready for E1. E1 is kind of also has its own special qualities.